For everybody showing up to the exams, this is the incredibly shrinking class. Questions? Nothing? Good? All right. Let's finish off strong induction. So, strong induction, again, the basis step is still the basis case. I like to say it that way, because the idea of proving for all n p of n, where the universe of discourse is, I'm just going to write it this way, n1, n2, n3, up to forever. Write it like that. So some sort of first, second, third, fourth element going on forever, and I want to prove this is true for all possible n. The basis case is still the same. We want to show that for the first element that the propositional function is true. Exact same thing as weak induction. All that changes for strong induction versus weak induction for the strong inductive case, we assume p of the first and p of the second element and everything up to p of the kth element, and then show p of the k plus first is true. So we assume all of those are true, and we just simply move on to the next. The only difference between strong and weak, again, weak is just that. Strong is everything up from the first element to the kth element is true, and then we move on. So we're going to use this for the existence for the fundamental theorem of arithmetic is that for every n greater than or equal to 2, n is prime, or a unique product of primes written in non-decreasing order. The concept of the fundamental theorem is simply this. It's like if I would write these things as products, the number 2 is obviously just a prime. The number 3 is obviously just a prime. The number 4 is the number 2 squared. The number 5 is obviously just a prime. The number 6 is 2 times 3, etc. For example, 12 is 2 squared times 3. And we can go on to say, I don't know, 26, 2 times 13. Really doesn't matter. What we're showing here is that every possible number n has inside of it a unique representation, a unique thumbprint for it, which is the primes that multiply to it uniquely. And so all numbers themselves are really just this skeletal structure of primes. So all that matters to us is primes. There's two things that we would have to prove. To prove, we would need first existence, which we haven't done yet, and that's what we're about to do. And the second thing we would do is usually uniqueness. Because we talk about product of primes, well, it better exist, and unique product of primes. So not only is it a product of primes, it's a unique product of primes. We've already done that one because we did that one by contradiction. We assume that there's a product of primes and another product of primes both equal to a number. And then what we did is we crossed out those primes that they shared in common. So we have unique primes on the left and unique primes on the right. Notice we have primes that are not the same on both sides. That leads to a contradiction. The only way that can possibly happen is if those primes actually divide 1. Really what that says is if you put the primes on both sides and cancel, the only thing left is the number 1, right? 1 equals 1, because they're identical is really how that works out. So we've already done that one. This is what we're about to do. To do existence, we need strong induction. Okay, so let's go ahead and prove existence. What I'm really asking to do is prove n is equal to some product of primes. Not unique, but just some primes multiply to every possible number. For all numbers n, there are some primes that will multiply together to make that n. I don't care what they are, just that they exist. Uniqueness was later. Normally the order would be prove existence then uniqueness, but we've already handled uniqueness. So in that we would say, okay, it exists. Not only does it exist, they're unique. All right, how to do that? Well, what I'm saying is for all numbers n greater than or equal to 2, n is equal to a product of primes or is prime, right? A prime number, if we look at like the number 2 and 3, why did I put those in parentheses? To make you have the understanding that this is a product. It's either a prime all by itself or a bunch of primes being multiplied. So we're okay. What's my universe of discourse? So this is my P, right? That's my propositional function that I'm talking about. What's the universe of discourse? What's my first element? So my first element is 2. So I have n equal to 2, then n equal to 3, then n equal to 4, and I'm just simply going on to infinity. So the universe of discourse I'm talking about is, what about the number 2? What about the number 3? What about the number 4? This is obviously a countable set. All right, I can't do for all n p of n here as is, so I'm going to use strong induction. So what's my basis? P of the first element. What am I doing? P of n equal to 2. Well, let's look at the number 2. What does that denote? P of n equal to 2 means what? 2 is prime or a product of prime. 2 is prime or a product of primes. Well, what is it? It's prime, so this is obviously true. The very first number that we deal with is a prime. We're good. All right, basis case is handled. Strong inductive. What am I assuming? That P of n equal to 2 and P of n equal to 3 and everything up to P of n equal to k. Is everybody okay with that? Start off at the first element, the second element, up to the kth element. So it's n equal to 2, n equal to 3, up to n equal to k. Assume all of that. What does that assumption actually mean?
That all the numbers from 2 to k are either prime or a product of primes.
Right, so 2 is either prime or a product of primes. 3 is either prime or a product of primes. 4 is either prime or a product of primes, right? That's what that is simply saying. So each are prime or a product of primes. What am I supposed to show? What's my goal?
K plus 1 must either be a prime or a product.
Show P of n equal to k plus 1. Which is k plus 1 is prime or product of primes. That's my goal. That's what I want to show. Well, all numbers n, no matter what. So let's go what we have. K plus 1 is, all numbers can be broken up into two versions. All numbers are either prime or they are not prime, which means composite. So that's just flat out. All numbers are either prime or composite. And so this would be, say, subcase 1, subcase 2, because inductive is an actual case of the larger proof. So normally you would say this is a subcase. All right, 1, k plus 1 is prime. Is my statement true? So if I accidentally land on a prime, it is prime. So, okay, fine. So we're true. Second version, what about k plus 1 is composite? What does that mean? What's a composite number? For example, why is 15, not 15, let's pick 36. Why is 36 composite?
Because it has other factors than 1 in itself.
There's numbers smaller than it that divide it, which would be 36. What divides that? Just give me two random.
6.
Right? 6 and 6, right? 6 times 6 is 36, so 36 has to be composite. All we know, the definition of composite means that k plus 1 is equal to a times b. What do I know about those factors for composites? What's always true about those numbers? They're smaller, right? What's the smallest that A and B can be? 2. That's as small as they could get. What's the largest they can get? 1 less. Right? All I know is that there's two numbers smaller. Now, obviously, we have other theorems that involve, like we go to the square root, da-da-da-da-da-da. But that was actually understanding that the fundamental theorem exists. Composite, the only thing that we have for the definition of composite is that there are two numbers smaller than this number that when they multiply become this number. Those numbers are not 1 and they are not the number itself, right? To be prime is it only has the factors of what? 1 and it. What does it mean to be not prime? Not that. 2 and less. Is everybody okay with that? Is everybody okay that this is where, because it's not prime, there has to be two numbers that are somewhere between 2 and k that multiply to become it? All right. Well, this is my inductive hypothesis. All numbers from 2 to k are what? Prime or a product of primes. What does that tell you about A and B?
Either prime or a product of primes.
So by inductive hypothesis, A is prime or a product of primes. B is prime or a product of primes. Well, wait a second. that would tell me that A times B is going to be what? If A is either a prime or a product of primes, B is either prime or a product of primes, if I replace them with what they're equal to, which is primes, what does that tell you about A times B? It must be a product of primes. If A was a prime and B was a prime, it's a product of primes. If A was a product of primes, you would take A's product of primes and B's product of primes and multiply them and get a product of primes. Is everybody okay with that? You would just stuff in A is a product of primes, plug it in it. B is a product of primes, plug it in it. I suppose I could write it this way. I don't know if maybe this would help. Is equal to prime or product of primes times, let's move this entire thing over, prime or product of primes. Obviously, this is product of primes. And obviously, our statement is true. So composites are actually what? A product of primes. Well, how did you know that? It's composite. There's two numbers smaller than it that multiply, both of which are a product of primes, therefore it must be. And so, again, this actually gives us a generator, right? What's 3? Prime. What's 4? Well, 4 is composite, and what multiplies it? 2 and 2. Well, 2 is a prime and 2 is a prime, so it's a product of primes. All right, what about 12? Well, 12 is 4 times 3. 4 was a product of primes, 2 and 2. 3 is a prime, so obviously 12 is a product of primes. All numbers just simply keep going on because they're either prime, or if they're composite, we could go down to what multiplied to it, grab their primes, move it back up. It's a prime, product of primes. So it gives us a generator. And then before, in a previous chapter, we proved that these product of primes are actually unique. Because if you found 2 of them, you actually found 1. Does everybody remember that? So those two together prove the fundamental theorem. All right. Let's try another one. Let's say I have a candy bar with n breakable pieces. In other words, I look at this, I have this big rectangle, and there's these little lines in it, right? And I can snap it. And I notice for my rectangle with these n pieces, right? One of the questions I have is, if I want to share this with n people, how many snaps do I have to do to share it with n people? So this is what I'm going to have to propose. What's your conjecture? How many snaps to break into the n pieces? Give me a conjecture on that. All right, we'll start off with this. N equal to 1. How many snaps do you have to do? None, you just eat it, right? N equal to 2 pieces. How many snaps? 1. N equal to 3. How many snaps? Say n equal to 4. I'm going to do it like this. how many snaps? If I snap it once, it would look like this. But then each of those are a n equal 2, which require 1 for each of those. So total is snaps are 3. Notice when I broke it, right, and then snap, snap, right? One break, here's an important feature. I broke it once. Now I broke it once, it became 2 objects of n equal 2. This one requires 1, this one requires 1, 1 for there, it became 3. Notice that every snap that you do is starting to do what? N equal to 5. Right, there's 5 pieces. I don't care where you break it, right? Let's say I break it here. I'm going to do one break, and it becomes this piece and then this piece. How many? This is back here at a 2-piece, right? This 2-piece required how many breaks? That requires 1. This is a 3-piece. We already know the answer. This one requires how many? It requires 2 breaks, because we already did that. All 3s require 2s. So how many total snaps did I do? 1, 2, 3, 4. Give me a conjecture.
Break it into n pieces, you need to snap it n minus 1 times.
Right. So it looks like my conjecture is n minus 1 snaps for n pieces. If there are n pieces in this object and you're going to break it, it's going to require you to do, and when I mean snaps, I mean you break it into 2 completely different pieces, which requires these straight edge breaks. This would be a trivial looking problem if everybody was just simply a vertical piece, right? If it was like this, if all of them looked like this, I think everybody would guarantee that 1, 1, 1, 1, 1, 1. Oh, 1 left over requires 0, right? It would be obvious that it takes 1 less snap than the number of pieces. You just break off 1 at a time. What's more interesting is, well, what if it's odd and you break it and there's so many pieces like this? So in this shape, we could use weak induction. Because you'd break off 1, and if you break off 1 piece, the rest is already k. If it's k plus 1, you break off 1, the rest is k. I'm going to do k, that's k minus 1. And k minus 1 plus 1 is k, so we're good. We could just use weak induction like that. But that's not going to happen for something that would allow a little bit more of an interesting shape. All right, so I'm going to prove it. What's your basis? P of how many pieces? 1 piece, right? Well, this piece requires how many? 0 snaps. So true, right? No snaps for 1 piece. Just leave it alone. It's unity. Strong inductive. What do I assume? That P of n equal to 1 and P of n equal to 2, and these are pieces, right? And everything up to P of n equal to k, each of these are what? Pieces, right? We require zero, 1, 2, up to n minus 1, sorry, k minus 1. Snaps. That's a k minus 1, that uses 1, that uses 0, right? One piece uses 0 snaps. 2 pieces requires 1 snap. K pieces requires K minus 1 snaps. So the rule works. That's what I assume. Show P of n equal to K plus 1. If I have a piece of chocolate, candy, that has these K plus 1 individual pieces in it, and I break it, and then I look at the two components, right? I do one snap. So I have my n equal to K plus 1, and I'm going to take one snap. What's going to happen? I have part 1 plus part 2. We have these two pieces that are still rectangular, right? What is true about their sizes? What's the least number I could break off? 1. What's the most I can break off, which would be the idea of leaving 1?
Okay.
Right? So if I have this, these pieces for their sizes, if this is size I, this is I pieces, and say this one is J pieces, both I and J are greater than or equal to 1, yet less than or equal to what? K. But because they're between, and the other thing that I know about this is what is I plus J? So I know this, and I know this. It's still K plus 1 pieces. It's just there's I over here and J over here. They're somewhere between 1 and K, but when I add them up, it's still K plus 1. Is everybody okay with that? All right. I requires how many snaps?
I minus 1.
Snaps for P1 are I minus 1. What about snaps for P2? J minus 1, right? Because it's J pieces. Why? By the inductive hypothesis. They're somewhere between 1 and K. It works. The number of snaps is always 1 less than the number of pieces I see there. So, how many snaps have occurred? Think about what I did up here on my building process. Can I prove by example? No. But does the example give me ideas? Yes. How many snaps did n equal 5 have? 1 plus 1 and 2. But why is the 1 and 2? Because the 1 had 2 pieces, which requires 1 snap. The other had 3 pieces, which requires 2 snaps. Add all the snaps together. 1 plus 2, I get 4. So, what are these snaps?
1 plus I minus 1.
For K plus 1, for n equal to K plus 1. Are 1 plus I minus 1 plus J minus 1. Right? Which is equal to what? I plus J minus 1. What's I plus J?
K plus 1.
K plus 1. K plus 1 minus 1. What's the answer? K. 1 fewer snaps than the number of objects? Yes. Yay, it still works. So we're done. Notice how we always do it the same way. You break it. I broke it into smaller pieces. The smaller pieces have the inductive hypothesis apply, therefore it works. Is everybody okay with that? Now I could reduce this problem to that a normal Hershey bar, which is for the one that's the smaller ones, where it's 1 piece, 1 piece, 1 piece, 1 piece, 1 piece, right? You just break off one at a time. Then you can reduce it to a weak induction problem. Because you break off one, there's K left over, the inductive rules, so okay. I'm going to have K minus 1 plus 1, that's K. So K plus 1 requires K. But this allows me to break it anywhere. I don't care where you break it, just snap it. Was that kind of surprising at first? When we started doing examples to get an idea, when you looked at it, do you think that, boy, if I had this bar like that, didn't you kind of think that if I break it down the middle and break a lot of them, I might have to use fewer snaps? And the answer is nope. Why? Because you broke it into two pieces. And now both of those have to have their own snaps that are involved again. So it's just the entire division. Even though you would think that I could get by with, if there's 15, maybe I could use 3 snaps and it breaks it all apart. The answer is no. If you wanted to do that, what would you do? You would actually fold, right? Put it back on top of itself and then do a one break that actually breaks through all the objects, which is why we use folding. All right. Let's try another one. I know my notation is different from the book. The book always does things like this, P of 1. And I do things like n equal 1. And I say P of first element and second element. The reason why I try to do that is to try to get you to realize that that number 1 is not the number 1. When the book writes it, they really mean first element and second element. So we have to think long and hard about particular problems on what it means, and as you go through it. Too often our examples are the number 1, the number 2, to the number 3, and so we get this little sticking point that's like, well, how does that all work? So let's play a variant of this, and we're going to play a game called NIM. And NIM is a game, in its most basic sense, is don't take the last object. If you take the last object, you lose. So the last thing there is a grenade, right? And it's yours. So kind of like hot potato, right? You take the last thing, oh, it's like, I lost. Suppose you can make it a grenade, and you really lose. And then it's a Monty Python skit. So, because the rabbits have big teeth. Probably one of my favorite things. Monty Python's funnier to talk about afterwards than when you're watching it. You're watching it, it's kind of funny. When you're talking about it afterwards, it's hilarious. And I don't know why. All right. NIM is you take the last equals lose. Let's put an R in it. Loser. All right. That's such a negative term. It sounds awesome. You take the last thing, you're going to lose. What we're going to do is normally NIM, there's several variations of this. So you would have large piles of stones and you start to take things and you have these rules like, okay, well, let's say I have a large number of stones and I only can touch one pile at a time. And I can take as many as one or as few as I want from a pile. So I can go to one pile and take one. I can take the whole pile. And what makes NIM played usually is within cultures that have a hard time with cardinality, right? They don't know how many to take. So if I have, or you just simply have so many individual piles everywhere, you can't count it. So that kind of makes it challenging. Like, so you walk in here and I have, there's a lot of piles of stones, and since you can't count it, the hope would be you would have things like, let's say there's only 2 piles of stones, right? And you're the second player. You look at this and say, I know how to make sure, and the first person goes, oh, I'm going to make it easy, and he grabs an entire pile. And so the second player is looking at, I have a whole pile of stones all by myself, and you just have to take the last one. I'll take them all but one. And then there's one stone left, the other guy loses, right? But as you start to have things that you can't count, so we aren't Rain Man, so you look at things, you can't count quickly, so you're like, I don't know how many, so you kind of randomly take until it gets down, until it's an easy problem, right? We can do a variant of that and say things like, this is like number 11, which is, you're playing, we only have one pile, but we're only going to allow you to take 1, 2, or 3. You can take 1, you can take 2, or you can take 3. Last person who takes loses. So we have one pile of n stones, or sticks, or matches. I don't know, what do they use? Matches? They use matches, but anyways. And you can take 1, 2, or 3. And whoever takes the last thing loses. All right? I cannot prove by example, right? But I can use examples to begin the idea of what I should do to play this game. So let's start off like this. N equal 1, player 1, player 2, player 1 goes first. N equal 1, what happens? And you have to take, you take, there's no take 0. It's take 1, take 2, take 3. There's 1 stone. What happens? Player 1 takes it. Player 1 loses. And so takes 1 equals lose. This guy wins. N equal 2. All right, this is important. Player 1 can take 1 or 2, but he's not stupid. We assume that the person's intelligent. He's playing to win. What would player 1 do? Why? Because I face player 2 with a 1 piece, and what happens if you face a 1 piece? You lose, right? That's the point. You shove the other person, that a 1 is a losing position. I know that because I've done that at the basics. So what do? Here's a new one. Well, I'm going to make that guy into the losing position. How do I do that? It's kind of like snapping, right? We snap off a piece, but we snap off a piece intelligently. I want to snap off a piece so the guy, what I give them is a loss. So I take 1, which means player 2 sees 1, so he loses, which means player 1 wins. So this is a win, this is a loss to him. Those look like the same thing. It's really useful when your W's look like your L's somehow. All right, N equal to 3.
Player 1's going to take 2.
I'm going to take 2. Player 2 sees a 1. He loses. This is another win column for me. N equal to 4. Take 3. Player 2 sees 1. He loses. This is a win. Boy, it looks like it might just be wins all the way down. Well, wait a second. N equal to 5. All right. This player 1 is the person who sees it, right? If player 1 sees a 4, he can win if he's not dumb. If he sees a 3, he'll win if he's not dumb. And if he sees a 2, he will win if he's not dumb. If he sees a 5, what can he take? 1, 2, or 3. If he takes a 1, what does player 2 see? A 4, which is a win for him. If he takes 2, he sees a 3, which is a win for him. If he takes 3, he sees 2, which is a win for him. So it doesn't matter what I do, I'm left putting him in a what? Winning position, which means I'm going to lose. But I would have to write those all down, right? You would have to sit there and say, okay, I could take 1, I could take 2, I could take 3, and then P2 sees 4, which means win. P2 sees 3, which means win. Which means P2 sees 2, which means win. Which means, but these are all the same object, so what does that mean? It's a loss. N equal to 6. Now, what are the losing positions? If I see a 1, I lose. If I see a 5, I lose. Now I see a 6. What should I do? Make him see a 5, which is a loss. So that's what I'll do. I'll go ahead and take 1, which means player 2 sees a 5, but that means he loses, so that's a win for me. Any guess on what the pattern does? lose, win, win, win. Lose, win, win, win. Lose, win, win, win. Is everybody okay with that? So it looks like the pattern, it seems, this is a conjecture, that for player 1 versus n, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc., is a loss, is a win, is a win, is a win, is a loss, is a win, is a win, is a win, is a loss, is a win, is a win, etc. Everybody catch the pattern? Give me a mathematical operator. Now I got to turn my conjecture into a proposition. Me saying it goes lose, win, 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 lose, win, 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 lose, win, win, win doesn't help me. Because I go, well, what if he has 1,002 stones? Crud. Lose, win, 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 lose, win, 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 lose, win, win. Can you get me a function that will spit out loss, win? What do I notice about the losses? They happen every 4 apart, right? They're every 4th. Is there a mathematical function that spits out things 4 apart? Yes. It's about congruency, which is based upon the, starts with an M, modulus, which is based upon the remainder, right? And I can write this however I want. I like modulus. What do I notice? If the mod of n and, well, might as well, let's do it the way the book does, sorry. N mod 4 equals 1. What numbers does that give? 4, 1, 5, 9, 13 means what? Lose. If you face n mod 4 and it returns a 1, you're in a losing position. On the other hand, if you face n mod 4 and it spits out, well, what are the other mods? 0, 2, and 3, you're going to win. So, here's a probability question. If I randomly throw stones down and you're player 1, there's 4 things that can happen. Lose, win, 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 right? What's your probability of losing? Well, how many losing possibilities are there? 1. And how many total possibilities? 4. So I have a 25% chance of losing and a 75% chance of winning if you're player 1. And, more importantly, you can count really fast. Right? Because if you can't count, we're toast. Well, not necessarily toast. You just start taking stones until, hopefully I can count faster than him, right? You start pulling out 3s, because it really doesn't matter. I don't know. Pull out, pull out, pull out. All right, wait. Okay, I count. I was like, whoever counts faster, you have a 75% chance of winning if you can count faster than them and you actually see something that's like, ugh. Or better yet, if you can count and he can't, you see it, even if you're a losing position, you'll take it and hope he hasn't counted yet and he just does something. Yay, he put himself into a losing position. Boom, I won. Right? So this is more of a speed counting thing. You put things down and you start counting really fast. And that's why if you actually wanted to play this, it's a really primitive game, right? It's really easy. If you want to play this, you put it on a timer. You drop down as many things as you couldn't possibly count, and then you have to take something every 2 seconds. You're fast enough, gotta go. Gotta take one. Gotta take one. So you're going and going and going until whoever can count faster than the other person. So, anyways. And the first person who counts usually will have the better chance of winning. It might be random if they both count the same rate, and it's like, yeah, you lost. Now, that's my conjecture. Prove it. So this is what I conject. This is my P of n. I believe this is true. How would I go about proving it? Strong induction. Basis. P of the first element. What is the first element? Darn it, 1. I keep picking examples. I always use the numbers 1, 2, 3. I should have thrown out some ones that have the odds or the every fifth or something like that. All right, is that true? What's 1 mod 4? 1, and it is a loss to person player facing it. So it's true. My modulus rule works at least for one stone. Inductive. What am I going to assume? I assume that this modulus rule works. You take the mod. If you see a 1, you're going to lose. If you see a 0, 2, or 3, you're going to win. I assume that this works for what? 1 stone, 2 stones, up to k stones. So when I say this, I assume that P of 1 stone and P of 2 stones, the book uses matches, or sticks, P of k stones all have our mod rule work, right? If you face one of these remainders, you're either going to win or lose according to our modulus rule. All right, I need to show P of k plus 1 stones that the rule still works. What is the rule? The rule says take the mod and then check the answer. Well, if I take the mod, we actually have 4 cases. If I would say k plus 1 mod 4, k plus 1 mod 4, k plus 1 mod 4, and k plus 1 mod 4 has 4 possibilities. I'm going to put them into, I'll take care of my wins first, right? What are my wins?
0, 2, 3.
0, 2, 3, and the last one is 1. Is everybody okay with me taking care of, what I did is the win cases, and I took care of the lose case separate. Is everybody okay with me splitting it that way? K plus 1 mod 4 is 0. Why is this a win? Why are any How did you make yourself have a win? You force them into a mod 1, right? A loss. For example, for what numbers do we have a mod 0? Like for here, which number is a mod 0 for the first 4 numbers? 4. What did you do for a 4? I took 3 to put them back into a mod 1, right? So what do you think I should do if I'm facing a mod 0? Take 3. So what I'm going to do is I will take 3 away. what does k plus 1 become? It'll become a k minus 2. What will the right-hand side become? Let's write as this thing. We'll move it. I'm going to move into congruencies. If I take away 3 from the right, what is that? Negative 3, right? So I took 3 from the k plus 1, and I took 3 from the 0, which is minus 3. But what is minus 3 congruent to under mod 4? That's actually a 1. So what happens? If I take 3, I've pushed them into a congruent to 1, which is a losing position. So player 2 loses. So I win. Yay! All right. My remainder was 2. Let's go way back to the beginning. Oh, I'm way over class. All right, so stop. Finish. And that will be your attendance. But what are you going to do? You're going to go back to what we did before and say, well, what would you do? I take 1, take 2, take 3, and then pick what you're supposed to do and show that for the first 3, you always send them to the 1, and for the 4th, it doesn't matter what you do. You take a 1, you take a 2, take a 3, you always leave them in a winning value. So, all right, that's it. So I look more like a math teacher today. The secretaries wanted us to dress up for a Halloween thing. And so actually this is what our former chair, he would always, like on Fridays, he would have jeans and it's kind of a shirt, but he would always have to meet with the dean. So in his office, he had this permanent jacket like this, pleat and a tie. So when he ever had to see the president or somebody like that, it'd be like, put that on, away he goes. So my problem is I don't have a very strong Russian accent. I need to speak Russian and then tell really unfunny math jokes. Yeah. I'm done teaching at 11:30. Sure. Next week as well. I mean.
Oh yeah. I'm gonna do it Friday.